Last talk of the day is from Wally from Stanford University, and he will be talking about design sensitivities in the case of multi-species reacting flows, and talking about the discrete adjoint framework that Wally has been working with, within the NEMO solver. So Wally, the floor is yours. You have 15 minutes. I'll let you know when you have 2 minutes left.
Perfect. It actually looks like I lost control here on my end.
Yeah, 1 second. Yeah, because you have it. It says we're not. Let me go back. All right, try again.
Okay. I think I'm good now.
Got it?
Okay. Yep, I think so. Fingers crossed. Yeah, so hi everyone. My name is Wally Maier. I'm a current PhD student under Professor Juan Alonso at Stanford, and I am happy to be the last presentation of the SU2 conference. It's a nice short hour-long presentation, so buckle up. I'm just kidding. So for my talk, I wanted to give a high-level overview of some of the developments of SU2 NEMO, and in particular, the coupling to the discrete adjoint and a verification and validation effort that's been undergone with that. And I'll also get into a little bit about the SU2 NEMO framework as a little bit of a primer for the requirements of the discrete adjoint. So with that, the design of hypersonic vehicles is slow, difficult, and most importantly, computationally expensive and monetarily expensive. The design of these vehicles can range from quote unquote low speed endo-atmospheric vehicles like the NASA X-43A, spoiler alert, the Top Gun Dark Star, all the way up to re-entry vehicles like the Space Shuttle, the Apollo capsule, or the Orion capsule. Each case undergoes a significantly different flight environment with different physics, different types of coupled phenomena that we need to take into account when we do our designs. Also, looking at some of the constraints in these designs, particularly in heat flux, we see a significant difference in the way we want to design our thermal protection systems. All in all, this puts a lot of strain on our computational tools. A lot of the computational tools that exist fall into two different categories. One, tools that are fast, however, they don't capture the adequate physics needed to see what's actually happening in the hypersonic flight regime. Or two, they do capture those physics, but they are incredibly slow and can't actually be used to run, hundreds of design iterations. So kind of touching upon some of these hypersonic physical phenomena, here's a chart here highlighting some of the things that we may see in the hypersonic environment. Down here, on the x-axis, we see flight speed in kilofeet per second. Thanks, US Air Force, using our units here. But around a flight speed of 5 kilofeet per second, we're starting to get to Mach 5, Mach 6. We start seeing what we call vibrational excitation. We start seeing molecules vibrating, taking energy away from the bulk flow. And as we get faster and faster, we start seeing molecules begin to dissociate, and then way up there in the entry regime, we start seeing flow ionization, and that's where we get our plasma sheath radio blackout type phenomena. The worst part about this when it comes to modeling in CFD is all of these effects are very highly coupled. Again, this is just kind of point out that modeling these hypersonic flows is very difficult, and to do that we need more powerful computational tools that are slower and really drag down the design process. So what does that look like in terms of aircraft design or vehicle design? So generally, this is what we expect to see. As we move up from conceptual design to detailed design, we expect to see a higher level of fidelity and higher level of cost as we get more detailed and more detailed. And as we do that, we also start losing design freedom. So less changes can be made further down the process we go. At least this is what we expect. In reality, this is kind of what we see. Either the computational cost in the preliminary design is much higher, and then the detailed design is very, very high, or we end up relying on low fidelity correlations. And while these are great for quick turnaround in the design process, we generally get a lower fidelity of design and less, or rather more conservative designs. So we're not really pushing the envelope there, which kind of brings me to the whole purpose of this work. So the development of SU2 NEMO, which was a framework that's been designed for hypersonic flow analysis, and now for hypersonic vehicle design, coupling with the discrete adjoint. So quickly, I'm going to go through some of the physical phenomena that we expect to see in hypersonic flow in a little bit more detail, and then get into some results. So SU2 NEMO, or the non-equilibrium models, I know you've probably heard a bunch about this now, is a robust and accurate simulation tool for hypersonic flow problems. It includes everything that you would expect to see in a hypersonic flow problem. So the thermochemical non-equilibrium, and recently turbulence models, which unfortunately I had to pick and choose which talk to give. The coupling with standard turbulence models, including the SA and SST models, which are implemented in a new branch. They also, SU2 NEMO has a flexible code architecture to allow us to quickly plug and play with different hypersonic flow models, gas models, including the mutation ++, and a suite of boundary conditions that Jacob had just mentioned a couple talks ago. I might have double clicked that. So to model hypersonic flows, well, we have to incorporate the thermochemical non-equilibrium effects. So as the temperature in the gas increases, energy is stored in different modes molecularly. Those modes include the translational, rotational, vibrational, and electronic modes. And to model this, we use Park's two-temperature model, which is a standard model in the hypersonic community. These energy modes are grouped into two temperatures, hence the name, the translational rotational temperature and the vibrational electronic temperature. So the translational and rotational temperatures and energy modes are assumed to be in equilibrium with each other, and the vibrational electronic modes are assumed to be in equilibrium with each other. However, both these sets are not in equilibrium with each other. Further, these temperature differences will also drive chemical reactions to take place, so we can see dissociation and new species being created or destroyed. So the standard Navier-Stokes equations is presented here. To account for all of these extensions to the Navier-Stokes equations, we go from these three equations, or rather 5 equations, if we take a three-dimensional problem, to something that looks more like this. So the continuity equation now includes a continuity, instead of one single continuity equation, we have a continuity equation for each individual species. So generally, we're looking at 5 additional equations just here, or rather 4. And we also have an additional vibrational electronic energy down below to track that extra energy contribution in the flow. So already we're extending our typical RANS 3D equation equations from 5 to 9, 10, if you want to get crazy, 30. So very clearly, we're getting much more computationally inefficient. So with that out of the way, I'll briefly touch on some of the past work done with the adjoint in hypersonic flow, particularly within SU2. So this work is built upon Sean Copeland's work, where he derived the continuous adjoint for hypersonic flows. This continuous adjoint required derivation of the governing equations for every single physical phenomena. This kind of made it prone to some derivation error, implementation error, as well as it was inflexible. So we weren't able to go and simply add the catalytic wall boundaries and then be ready to go. We had to rederive that, and we also had to make sure that we were properly capturing the coupling that occurs between those boundary conditions and the numerical schemes. So that's all avoided with the coupling to the discrete adjoint. So now it's a very much sort of black box kind of functionality where we can track those variables through the entire process without having to rederive anything. So with that, I'm going to briefly go over some of the results of the discrete adjoint as a verification effort. So in these cases, what we're going to be doing is comparing the discrete adjoint to a finite difference formulation to compare the design sensitivities. So this first case is an HTV2 like boost glide vehicle. So essentially this is a long endurance, high speed vehicle where we expect to see not powered, but it goes through long endurance, the flight. So with this, we were using the NEMO Air 7 gas model. So we include a weakly ionized flow. And to parameterize it, we used the FFD boxes. There's 120 FFD boxes. And it was a Mach 17 case at an angle of attack of 30 degrees. So here's just a couple of little pictures of eye candy of Mach contours. We can see nice pretty shock waves below the surface and a little bit of recirculation coming around the aft end of the vehicle. Here is a comparison of the finite difference formulation of the design sensitivities to the discrete adjoint. And as you can see on the graph on the left, we are nearly identical from discrete adjoint to finite difference. So we can say here that the discrete adjoint is coupled properly, and we are predicting the appropriate design sensitivities with the discrete adjoint, which is great news, especially this includes capturing the chemistry, non-equilibrium effects, etc. On the right, we can see a surface map of the drag sensitivity. And it's, again, physically, this kind of makes sense. All of these sensitivities are with respect to essentially extending the plan form of this vehicle. So if we make this vehicle and extend it, make it larger towards its angle of attack, we expect to see a larger drag. So that's why we see those high sensitivities along the leading edges of this vehicle. Next, we have a Mach 8 viscous cylinder. So this is using a 5-species gas model with the Wilkes-Blattner-Eucken transport model. This is also run with the SA turbulence model. So it's kind of running the full gamut here. And instead of looking at coefficient of drag, we'll be looking at the total heat flux along the body, as heat flux is arguably the most important thing to look at in hypersonic vehicle design. So with that,
Wally, you have 2 minutes.
Perfect. So here again, we have some of our pretty eye candy pictures, temperature contours on the left and Mach contours on the right. One thing to notice here is on the Mach contours, where we start to see the re-acceleration of the flow. Just remember, it's right around 45 degrees of an angle with respect to the center. So here again on the left is our computation of or comparison rather, of the total heat flux we see on the wall. Again, we see a very good agreement once we get to a smaller step size. The finite difference with a step size of about 1 millimeter, we see a pretty significant difference with respect to the discrete adjoint. However, creating a smaller step size, we see a much better agreement. And on the right here, we see, at the top right, we see the adjoint density. So this is the where the flow solution is most affected, or the heat flux is most affected, and we expect to see everything ahead of the cylinder, because we're in hypersonic flow, so all the flow characteristics are coming from right to left. And lastly, at the bottom right, we see the surface sensitivity magnitude. So where the surface is most sensitive, or the heat flux is most sensitive to surface perturbations. Again, we see the nose, or rather the stagnation point, which makes sense. But we also see right around that 45-degree mark, we start seeing a pretty high sensitivity. And this makes sense because this is where the flow begins to re-accelerate around the body. With that, some conclusions. The SU2 NEMO code suite has been successfully coupled to the discrete adjoint for 2D and 3D problems with various objective functions. Further testing is ongoing for coupling to the turbulence models, particularly some of the two equation SST models. Some future work includes coupling the mutation plus library to the CODI and MEDI suites. Right now, it's incompatible. And lastly, I'm in the process of making a SU2 NEMO tutorial, which has been put off for way too long. And with that, I'd like to thank the SU2 community, the SU2 NEMO community for all their help and support. And lastly, I'd like to ask y'all, somebody to eat a pizza for me. Sad to not make it to Italy, so someone has to enjoy one. So with that, I'll take any questions.
Thank you very much, Wally. Thank you. We have minutes for questions. Anyone?
Hi. So, first one is the observation. You show the step size required and use fine. You're trying increasing the step size to go closer to the discrete adjoint, and my experience is not enough. The question is, for the three tests that you showed, we not see the response. How many use of English you need to reach?
Okay, the question, Wally, is about for each one of the test cases showing the number of iterations needed to reach convergence towards an optimal solution, if you did that.
So the work that I did was, there was no actual design optimization. So it was a single run. So I ran the primal solution and then I ran the adjoint solution. Regarding the convergence of just the solution, I can post those. I don't have them currently, but there was no actual, optimized design per something. It was just looking at the sensitivities to make sure the framework was working appropriately.
So building block towards making the full design, exactly, the full yes. Optimal design. Yeah, thank you. Mm-hmm. Any other questions? Okay. Okay, sorry, I couldn't hear who's distracted.
So, Wally, the question is there anything related to OpenMP or hybrid in what you've done? And if not, is there interest
in that direction?
The answer is always, I don't understand so much the parallelization, but definitely always looking to speed up the code. As many of you may know, SU2 NEMO is just a little bit slower. Actually, it's a lot slower than the perfect ideal gas solver. So looking for speed ups is always great. So there would be interest. I don't know if I have time to do it, but yeah, I'm kind of following the typical SU2 developments and trying to move over some of the great capabilities introduced back into SU2 NEMO.
Thank you, Wally. Any other question from the audience here in presence? If not, there are a couple of questions from people connected remotely, Wally. The first one, and I'm reading it, is what numerical settings strategy did you use to get converged solutions, let's say a steady state run? And how many iterations did it take for a typical test case?
Sorry, I missed that first part of the question.
Yeah, sorry. Yeah, the first part is my interpretation is referring to the possibly numerical scheme and numerical setting used to converge the CFD solutions.
Yeah, so generally for these problems, we like to use the AUSM schemes to get a nice shockwave capturing behavior, not too smeared. And then you would run first order for a while until we have a fairly converged solution and move over to a second order scheme. However, if that doesn't work, using modified stagger warming is a pretty solid bet. Regarding the iterations, it depends on the type of problem. With a Euler or NEMO Euler case, they converge fairly quickly. I believe I could get convergence within 5,000 to 10,000 iterations for the HTV2 case, which maybe one more here. So for this case, it took about 5,000 to 10,000 iterations, whereas the cylinder took maybe around 40,000 iterations from memory. When it comes to viscous problems, the stiff chemistry equations are often, it takes a while to resolve the boundary layer. And work is being done to speed that up using the implicit Jacobian. The Jacobians are there. There are some tricks that I think we need to play in the solver development to make sure that we have proper stability with those before it's something that we can run with very high CFLs.
Great, thank you, Wally. There is another question from people remotely connected, and it is this. Does the SU2 NEMO library included in the latest version of SU2, or is still closed for the public? Maybe I can answer to this question, Wally, if it's okay for you, and then I can follow up with a question for you then. So the SU2 solver is openly available, is included in the latest release. You can find it in the master branch, in the developer branch, and that is openly available. If you cannot find it, please give us a shout and we will be able to guide you. But maybe, Wally, the question could be, is all your work related to this discrete adjoint formulation, implementation, and so on, available online on the public GitHub, or is still on a private branch?
Yeah, so the discrete adjoint is soon to be on the public branch. I am going through and trying to make the code pretty. so it passes the pull requests, but it'll be available shortly. Not yet, but I'm hoping within the next month. Yeah.
Awesome. Great. I don't see any more questions from people connected remotely. Is there any very last minute, last question, last chance here? Like, okay, then I guess we can thank again Wally for his talk.